Hello, in this video I'm going to do a lot of example problems for the moles test. So it's sort of a moles test review full of example problems. What we learned about the concept of a mole, the molar mass of a compound, we learned about mole conversions, percent composition, and empirical versus molecular formulas. So let's start with the concepts involved in the idea of a mole. First, the mole is a measurement of what? Is it a measurement of mass, quantity or number, value, or physical size? Well, a mole just tells you how many things you have. It is a measurement of quantity, specifically the quantity 602 billion trillion. So it measures number. Now, a mole of something will have a particular mass, and it will have a particular value and a particular size, but a mole of apples is going to have a different mass than a mole of hydrogen. So mole itself is not a measurement of mass, even though a mole of something can have a mass. Mole itself is a measurement of pure number. So Avogadro's number, which is 6.02 times 10 to the 23rd, it can be used to count groups of what? To count groups of atoms, molecules, elephants, or anything. Well, Avogadro's number can count groups of literally anything at all. You could count groups of atoms or molecules. This is common because you deal with this many of them on a daily basis. But you could theoretically count 602 billion trillion elephants or dollars or planets. So it can be used theoretically to measure anything at all, even though it's only useful to measure molecules and atoms. 1 mole of NH4F is equal to what? 37-ish grams, 6.02 times 10 to the 23rd particles, 6.02 times 10 to the 23rd molecules, or all the above. So while 1 mole technically is this number of something, so B and C are right because of the right number, 1 mole of this particular chemical actually has a specific weight. So 1 mole of this chemical has a mass equal to the molar mass of this chemical, which happens to be 37.073 grams. So in this case, these are all actually correct. 1 mole by itself is not a measurement of mass, but 1 mole of a particular substance will have a particular mass called the molar mass. So this is right because it's the molar mass of this specific chemical. These two are right because the mole is always equal to that number, Avogadro's number. So all the above. What property would 1 mole of H2O and 1 mole of CaCl2 have in common? So you have 1 mole of this chemical and 1 mole of that chemical. What would they have in common? Would they have the same temperature, the same volume, the same number of particles, or the same mass? Well, we just said that mole is a measurement of number. So if you have 1 mole of each of them, you will have the same number of them. They're going to weigh different amounts. They're going to be maybe different temperatures, I don't know. They may have different sizes, which is the volume, but the number of particles will be the same because 1 mole is always 602 billion trillion. So this is the answer. What number of particles is the same? So which non-scientific number is closest to Avogadro's number, which is 6.02 times 10 to the 23rd? Is this close to 6,000, 0.006, 6 billion trillion, or 6 million? Well, this number represents 6.02 and then 21 zeros after the decimal place. So this is a lot. This is a huge, huge number. It's the closest to 600 billion trillion out of all these examples. Yep, 600 billion trillion. I don't know why I had that twice. That's the answer. There we go. So now on to some questions about the molar mass of compounds. What is the molar mass of C2H3O2? You can't solve it by itself. You actually have to look at something else. But it's going to be 2 times the molar mass of carbon plus 3 times the molar mass of hydrogen plus 2 times the molar mass of oxygen. And these individual atoms, you can find their masses on the periodic table. So to get the molar mass of this compound, you would take 2 copies of carbon, 3 copies of hydrogen, and 2 copies of oxygen, and get the masses of those. So let's look at the table. Carbon weighs 12.01, oxygen weighs 15.99, and hydrogen weighs 1.008. So where we see the mass of carbon, hydrogen, and oxygen, we will plug in these numbers and get this expression. So you can just put this into a calculator, and you will get 59.044 grams. So this is the molar mass of this chemical. What about this chemical? Ba3PO42. So similarly, you just have to count the number of atoms you have. This one is a little bit annoying because we have a polyatomic ion, and hopefully you remember that in this chemical I have 3 bariums, I have 2 times 1 phosphoruses, and 2 times 4 oxygens, because this 2 gets distributed basically to everything in here. So I have 3 bariums, 2 phosphoruses, and 8 oxygen atoms that I want to measure. So I got to figure out the mass of barium, phosphorus, and oxygen. There's barium, there's phosphorus, there's oxygen. I plug those numbers in. So barium goes there, oxygen goes there, phosphorus goes there. That ends up being this expression. So you just put this into a calculator, and you get that the answer is 601.924 grams. So that is the molar mass of this chemical. You may also see it as grams per mole. The number is what you want to look for here. The unit could be grams or grams per mole, depending on the problem. So that's how you get the molar masses. Now on to mole conversions. How many grams are there in 3 moles of fluorine? So if you can use your notes, you can just pull out this molar map right here, which tells you how to go from one thing into another thing. To leave moles, you want to multiply. To go into moles, you want to divide. And if you're dealing with mass, you divide by the molar mass. And if you're dealing with particle number, you divide by Avogadro's number, right here. So in this case, we start with 3 moles of fluorine. That's the number that we get, so we will start here. And you want to know how many grams are in it, which is a measurement of mass. So we are going from moles to mass. And if you follow the arrow, it says we multiply by the molar mass. So we take 3, we multiply by the molar mass to get the answer. Specifically, this is the molar mass of fluorine, so we have to look that up on the periodic table. Fluorine is right here. The molar mass is 18.998. So you put that into a calculator, and you get your answer, 56.994 grams. So calculate the number of molecules in 3.2 mol of CaCl2. Maybe you haven't seen this, but mol is short for moles, not molecules. So this says how many molecules are in 3.2 moles of calcium chloride. So you are going out of moles, because it tells you how many moles you have. You're going into molecules, which is a particle. Atoms, molecules, these are all particles, so you're going this way. Follow the arrow. It looks like to go from moles to particles. You multiply by 6.02 times 10 to the 23rd. So we'll take 3.2, multiply it by 6.02 times 10 to the 23rd to get the answer. Put that into a calculator, and you get 1.06 times 10 to the 24th molecules. How many moles of neon do you have if you have 3.67 times 10 to the 21 atoms of neon? So an atom and a molecule, they're both particles. So we're going to start with particles and go into moles, because that's what I want to find. To go from particles to moles, well, you're going into moles, so you will divide. And because you're dealing with particle number, you divide by Avogadro's number right here. So you take the number, divide it by Avogadro's number, and you get your answer. If you just put this into a calculator, you will get 0.0061 moles. So it's not very many, but that's okay. That doesn't mean that it's the wrong answer. 0.0061 moles of neon, that's how much you would have if you had this many atoms. Calculate the mass in grams of 0.078 moles of FeOH3. The molar mass is 106.9 grams per mole. So you can look at the map. You are going out of moles, because it gives you the number of moles, out of moles into the mass. And so the arrow going from moles to mass as you multiply by the molar mass. Generally, if you leave moles, you multiply. If you go into moles, you divide. So we're leaving moles, you multiply by the molar mass. And we might have to calculate it, because this isn't an atom. We can't look it up. We would have to calculate that molar mass, but it actually tells it to us, which is convenient, 106.9. So what we do is we multiply by the molar mass. So you multiply the number by the molar mass, put that into a calculator, you'll get 8.3382 grams. Maybe you can round this, but this is the exact answer. Determine the mass of 3.234 times 10 to the 24th particles of CH4. The molar mass of CH4 is 16.04 grams per mole. Nice of them to give us the molar mass. So in this case, we have a number of particles, and we want to figure out the mass. Now this is going to be a little bit annoying, because there is no direct way to go from particle number to mass. You have to go through a middle step. You start with particle number. You're going to have to move down to moles, and then move up to mass. So you're going to have to do 2 different things. To go into moles, you divide by 6.02 times 10 to the 23rd. And to go from moles to mass, you multiply by the molar mass. So we have 2 steps. We are first going to take our number and divide it by 6.02 times 10 to the 23rd, then multiply by the molar mass. Now we might have to calculate this, but in this case we don't, because they give it to us. 16.04. So that number goes into the molar mass. We just put this whole thing into a calculator. We don't have to worry about it. And the answer is 86.17 grams. How many moles of K2O are in 135.5 grams of K2O? Hopefully you get the idea at this point. We're going out of grams, so out of mass. We're going into moles, so we'll probably divide. Let's see. we are going out of mass into moles. The arrow going in that direction says you divide by the molar mass. Now, in this case, they didn't actually tell us the molar mass. This is K2O, so we can't just look it up. We have to calculate it. This has 2 Ks and 1 O. So what we're going to do is we're going to take 2 times the mass of K and 1 times the mass of O. Look it up on the periodic table. Potassium is right here, 39.098. Oxygen is right here, 15.999. So we have 2 times potassium's mass plus 1 plus oxygen's mass. Get that number, 94.195. So then you put this into a calculator and you get your answer. 1.44 moles. How many moles are in 6.66 grams of Na2O? So we'll, once again, go out of moles and into mass. That's grams. So we're going to multiply by the molar mass. Or wait, we're going out of grams and we're going into moles. Sorry, because it tells us how many grams we have. We go into moles, right? So mass into moles, because that's our answer. This is what the question gives us. So we're going from mass to moles that way, so we divide by the molar mass. So you actually have to figure out what the molar mass of Na2O is. I have 2 sodiums and 1 oxygen. So the molar mass is going to have 2 copies of sodium and 1 copy of oxygen. Sodium is right there. It's about 23. Oxygen is right there. It's about 16. So you put this into a calculator, figure out that the molar mass is 61.979, then you do the division. 0.017 moles. It's totally fine to get a number less than 1. So that's the answer. A lab scientist needs 0.68 moles of LiOH to use in a medicine. What mass of powder should they measure on the scale if they need this many moles? So this is a problem where we start with a number of moles and we need to end with a mass. So we're leaving moles going into mass. We're probably going to multiply. Leaving moles going into mass, we multiply by the molar mass because we're going from moles to mass. So we take this number and we multiply it by the molar mass of the chemical. We have to figure out the molar mass because the problem does not tell us. This has 1 lithium, 1 oxygen, and 1 hydrogen. So we will take 1 of the mass of lithium plus 1 oxygen plus 1 hydrogen. All those added together is the molar mass. We look it up. Lithium, hydrogen, oxygen. So you plug those numbers in. This ends up being 23.948. You do the multiplication, and you get your answer. 16.285 grams. Almost done with these. What would be the mass of 1.92 times 10 to the 23rd atoms of nickel? Now, hopefully you know the routine. They give us a number of atoms, so we're going to start with particle number, because this is how many atoms we have. Atom is a particle. We want to get to the mass. There's no direct way to do that. We have to go through moles. So we're going to go here from particle number to moles by dividing by Avogadro's number. Then we're going to go from moles to mass by multiplying by the molar mass. So you just follow the arrows. We divide by Avogadro's number, and we multiply by the molar mass, specifically the molar mass of nickel. So let's look that up on the periodic table. It's about 59. It's 58.693. So you put this whole thing into a calculator. You don't have to think about it. The answer is 18.72 grams. Last one. Calculate the number of atoms in 6.25 grams of magnesium. So you start with a number of grams of magnesium, that's a mass, and you go to a number of atoms, that's a number of particles. So we start with a mass. We want to go to particle number. We're going to need 2 steps. We're going to need to jump to moles and then to particle number. So to go from mass to moles, you follow this blue arrow. You divide by the molar mass. To go from moles to particle number, you follow this red arrow. You multiply by 6.02 times 10 to the 23rd. So we're going to do this and then this, just following the arrows. Now, dividing by the molar mass of magnesium isn't easy unless we know what the molar mass of magnesium is, so let's look it up. It's 24.305. So that number goes here. Put this into a calculator, and you will get 1.55 times 10 to the 23rd power. So that's the answer. This is how many atoms there are in 6.25 grams of magnesium. Next, we learned about percent composition. The way that you determine the percent composition of a chemical is you measure just the mass of one particular part of the molecule, divide it by the whole molecule, then multiply it by 100 to make it a percent. So if I asked you for the percent composition of a chemical, you would have to give me all of them, but I might just ask you for one part of the chemical. In this case, the percent composition of phosphorus in this whole thing is just the mass of just the phosphorus part divided by the total molar mass. So we know how to get the total molar mass. You take 3 copies of hydrogen, 1 copy of phosphorus, 4 copies of oxygen. So that's the total molar mass on the bottom. And the phosphorus part, in this case, is just 1 phosphorus atom. So we have that 1 phosphorus atom, which is the phosphorus part of the molar mass. We divide it by the whole molar mass. That gives us our percentage. So we have to look up phosphorus, hydrogen, and oxygen's mass. Phosphorus is about 31. Oxygen is about 16. Hydrogen is about 1. So we plug those numbers in. We just put this into a calculator. Even though it looks big, we don't have to worry about it. And we get 0.316. Now this is almost the answer, but we want a percent composition. This right here is a ratio. So we need to multiply it by 100 to make it a percent. And that ends up being 31.6% of this chemical is made of phosphorus. Now this is the mass of the chemical, not the number of atoms. So there are 1, 2, 3, 4, 5, 6, 7, 8 chemicals. It's not like 1/8 of it is phosphorus, just because 1 atom out of the 8 is phosphorus. This is the mass contribution, and because these all weigh different amounts, the mass contribution and the atomic number contribution is not exactly going to be the same. So what's the percent composition of iron in Fe2SO43? Now, this is the same kind of thing. What we have to do is we have to take the mass of just the iron part, divide it by the mass of the whole chemical, then multiply it by 100 to make it a percent. So we need to get the mass of just the iron part, divided by the whole chemical, times 100. In this case, we have 2 copies of the iron atom. We have 3 copies of this whole thing, and that means we have 3 sulfurs, and 4 times 3 oxygens. So in this case, we have 2 irons, 3 sulfurs, 12 oxygens, because that's 4 times 3. Now, all we have to do is look these up on the periodic table. Iron, sulfur, and oxygen. Iron is about 56, sulfur is about 32, oxygen is about 16. So we plug those numbers in. This looks big, but all we have to do is put it into a calculator. We don't have to worry about it. We get 0.279. Now this is almost the answer, but we want a percent composition. So to turn this decimal into a percent, we multiply by 100, and we get 27.9% of this chemical is made of iron by mass. Now we get to the easiest part, empirical and molecular formulas. So which one of these represents the simplest whole number ratio of the elements in a compound? Which one of these is the simplified version of the chemical formula? And the simplified version is going to be the empirical formula. So if you have something like C2H2, this is not simplified because both of these are divisible by 2. The empirical formula would actually just be CH in this case. I don't think that's a real chemical, but it would just be CH. So true or false? In an empirical formula, it tells you all the atoms in a chemical, not just the ratios. True or false, the empirical formula gives you all the atoms. Well, I just said it, that's actually false. The empirical formula only gives you the ratio. The molecular formula gives you all the atoms. So the empirical formula is just the simplest ratio. So you got to know which one is empirical, the simplest version, which one is the whole thing, molecular version. So of the following formulas, shouldn't say molecular formula, so the following formulas, which one could be an empirical formula? Well, you have to remember that the empirical formula is simplified. So you look at the subscripts of the chemical, and if they have any common divisor, if you can simplify them, then it's not empirical. So this is not empirical because this is 2 and 4. You could divide these both by 2. So this could be CH2. That would be the empirical formula version of this. This one is actually empirical because 1 and 4, there's no common divisors. So that's the answer. The other ones all have common divisors. 2 and 2, you could divide those both by 2. 2 and 2, you could divide those both by 2. So CH4 could be an empirical formula because it's not, there are no multiples in the subscripts. It's simplified. What would be the empirical formula for H2O2? Well, in this case, you would look at the 2 and the 2, figure out the number they're both divisible by. Now, 2 and 2 are both divisible by 2, so you could divide that by 2, divide that by 2, to simplify it, basically, and you would get just HO. This is not right, because this ratio is not 2 to 1, it's 2 to 2, right? So this is not simplified, this is not simplified, this is not simplified. This is the simplified version that actually matches this, where you divide that by 2 and you divide that by 2. Which of the following could be the molecular formula for a chemical that has the empirical formula FeS5? Now, the molecular formula has to be some multiple of this, right? Because maybe originally, this was like a 2 and this was a 10, or maybe originally this was a 3 and this was a 15, but the subscript that actually is on this and this, they have to have a common multiple, right? And it has to be related. One of these is 5 of these. So we have to find the answer that has a ratio of 1 to 5. In this case, 2 to 37. It's not like 2 divides into 37 5 times, so it's not that. FES10. Now, it's not that, because if we were going to take these subscript numbers, the 1 and the 5, and multiply them by something, so maybe we have like FE2S10 or FE3S15, the way we get all these possible answers is by taking the subscripts and multiplying them by the same number. So we can multiply these by like 2 to get that, and 3 to get that. But they got to be multiplied by the same number. And this one right here can't turn into that by simplifying. Anyway, now we have Fe2S10. This is actually going to be the answer, because this 2 and the 10, you could simplify this by dividing both of these by 2. And if you simplify this chemical by dividing both the subscripts by 2, then you actually get FeS5. So this is the answer, because this simplifies into this one. That was it. That has questions over everything you have to know for the test. I hope this is helpful.